So welcome. So we're going to continue with our study of statics and dynamics. We've done statics so far, and the statics that we did was specifically we talked about doing the famous traffic light problems where we have a traffic light that's suspended from two wires. But that's not the only type of statics we can have. We can also have statics where we have a block resting on a slope. And we can have statics with a block which is moving at a constant velocity down a slope. That's also statics. Remember, statics is about not accelerating. It's not about not moving. It's about not accelerating. Now, the problem with these latter two examples is that we don't really have the vocabulary and the math underpinning to be able to do these things because there's going to be friction involved in these two guys. So we need to learn a little bit about friction. So we start off, we talk a little bit about friction and the normal force, and then we start talking about statics and dynamics with friction, and then we'll go on. So frictional force and normal force.
We're actually on part 3. We've been through this.
Okay, oh, thank you ever so much. So basically we can divide this reaction force into a normal and a frictional component, and we can learn a little bit about friction from looking at the two ways. There's static friction, which means not moving, and kinetic friction, which means moving. And we have two slightly different equations, but there's two coefficients of friction to deal with that. And then we did these guys, I think, yeah? And we're on to this bit now, yes? So let me have a quick look back. So we had finished with that. So now let's talk about dynamics. I'm going to actually talk about dynamics without friction to begin with, because we've not done one yet. So I'm going to find a blank page, and you get a blank page, and we'll just, rather than going back to the previous chapter, we'll just do the problem I was going to show you, or a similar one. The classic setup for a dynamics problem is a table with a massless, frictionless pulley, and on top of this we put a block, and suspended here we have a load, and we have a piece of string that connects the two. And this table is frictionless. Well, I really should say the interface between the table and the block is frictionless, because it's always it's always the double thing. It's always, you know, you've got to have both of them behaving. Sometimes said smooth. It's not really, you shouldn't really say smooth, because smooth surfaces can be quite friction filled, but let's say frictionless. I know that there's a weight here. This is going to be mg, where that is little m. And I know there's going to be a kind of a tension force pulling back on this load. If not, it would just accelerate downwards at 10 meters per second squared. It's in free fall, so there must be something pulling back. And I know that there must be something pulling on this block to get it to move forwards, and that's the tension. And I know that there's a weight here, that's big mg, and I know that there's a normal force there. But I know that these are at 90 degrees to the direction of motion. I know there's no force pulling back because there's no friction. I know that this tension here equals that tension there because they form an action-reaction pair. So, okay, I'm kind of in business. It's a bit complicated. It gets confusing because on the horizontal we tend to say moving to the right is positive, moving to the left is negative. and vertical means moving to up is positive and moving down is negative. But if you think about it, this motion is downwards once you go beyond the pulley, which is like negative motion, but it's to the right before you get to the pulley, which is positive motion. So positive motion becomes negative motion, and that's a disaster. That's going to be an awful thing. So the first thing we learn to do is redraw this diagram. And let's put some masses in here. Let's say that this here is 4 kilograms. And let's say that this guy here is 6 kilograms. I'm just making those up. So 4 goes in there and 6 goes in there. And that's tension. And that's tension. I don't care about the normal force and the weight of the block because they're at 90 degrees to my motion. So I don't care about that. Not for the minute anyway. And I know that this is going to be 60 newtons because, you know, mg. Cool. There's 2 questions I can ask you. One question is, what is the tension once the object is released? And the other one is, what is the acceleration? Acceleration of the 6 kilogram mass, or the acceleration of the 4 kilogram mass, or the acceleration of the system, or the acceleration of the piece of string. It's all the same acceleration. If it wasn't, then the things would get further away from each other or they'd collide, and they don't do either. So the accelerations are the same for all those parts. So I can ask you about any one of them or all of them. It's just acceleration is acceleration. If I asked you, looking back at this first diagram, if I asked you, given a 6 kilogram load and a 4 kilogram mass, if I said, what's the value of tension before I release the system? So I got my fingers on the table holding that B, I'm holding the block back. Can anybody tell me what the tension in the string would be under those circumstances? Just by observation. It's going to be 60 newtons, isn't it? Because the downwards force is balanced by the upwards force because it's in equilibrium. You'd say the sum of the forces vertically for the load equals 0, and you're off to the races. Yeah. If I cut the string, what would the acceleration of the load be? What's the acceleration of that load if I just cut the string and let the thing go? What would the acceleration be? Be negative 10 meters per second squared. Yeah, be just free fall. Yeah. I'm going to let the system go, but I'm not going to cut the string. So, does this block add anything to the gravitational pull on the load? It's just independent, isn't it? But does the block add inertia to the entire system? If I have the same force but more inertia, I must have a lower acceleration. If I had 1 billion kilograms on the table, on the block, I would accelerate because it's a smooth interface, but incredibly slowly, incredibly slight acceleration, because 6 kilograms versus 1 billion kilograms is not much. If I had 1 billion kilograms in the load and 4 kilograms on the block, I'd be going at pretty much 9.8 meters, 9.8 or 10 meters per second squared. I'm usually somewhere in between. So if for the acceleration you get a value which is greater than 10 or less than 0, watch out. You've got to be in that window somewhere. There's a number of ways of doing this. I'm going to show what I think is the most efficient way. So the first thing you do is you draw yourself a decent diagram. And then let's say, it turns out you've got to find the acceleration on the way to finding the tension. So I might as well teach you how to find the tension. Because in doing that, I'll teach you how to find the acceleration. So find T. So find T using, well, there's a T there and a T there. Oh, the sum of the forces on the 4 kilogram is equal to the mass of the 4 kilogram times the acceleration of the 4 kilograms. Looking at my diagram, I say plus T. There's nothing going the other way. Remember, we're resolving forces along a line. We're still doing Newton's laws. It's just the string is a piece of magic that lets the forces go around corners. It's like there's nothing else lets the tension force go around a corner, but a piece of string does. So T is equal to, well, the mass times the acceleration of the fall. I could solve this if I knew the acceleration, but I don't know the acceleration. I say the acceleration of the 4 is equal to the acceleration of the 6, which equals the acceleration of the system. That's a conceptual observation, if you like. And I say find acceleration system using, well, let's change coloured pens so you can see exactly what I'm thinking here. I would say, there's my system. The sum of the forces on the system is equal to the mass of the system times the acceleration of the system. So now I'm looking at my diagram. I'm going at plus 60 is equal to, I like to put down 4 plus 6 so that I know that I did add them together. When I'm visually checking my answer, I can easily say, oh, 4 plus 6, yeah, I know what I did. Times A system. So A system is equal to 60 over 10, which equals 6 meters per second squared. T is equal to 4 times A4, which equals 4 times 6, which equals 24 newtons. So there it is. Can you see that okay? I worry about this thing being in the way. Can you see okay? Can you see okay? I wish that kind of raise the screen, but if I ask you for the acceleration, you do the bit that's in purple. If I ask you for the tension, you do all of it. Yeah. So it's very set, very standard, very set way of doing these things. Got to do a stretch diagram if you get confused about the signs, then you just run it. Questions? I want to do another one. I'm going to find another blank. There's another blank. Find yourself another blank piece of paper. We're going to do something very similar. So now we've got a smooth, frictionless, I got a smooth table. Let's do it again. Let's do 6 here. Let's do 4 there. It looks at first glance like it's the same diagram, but it's not. Because, I'm going to put this in a different colour so you can see it. Because my 40 newtons and my normal force, that 40 newtons is not perpendicular to the motion. In the last one it was, so I could ignore it. But now it's not, so I can't ignore it. That 40 newtons will give me a backwards component, and this is going to be 40 sine 30. And can you see how I'm kind of helped because I didn't do a 45-degree diagram, so that little angle there is the same as that little angle there. It's pretty obvious it is. That's 40, that's 60 in that triangle. That's 60, that's 30 in that triangle. So after a while you realize, oh, I can just say if that's 30, this is going to be 40 sine 30. If this was 25, it would be 40 times 25. If it was 15, it would be 40 sine 15, and so on. It's the same diagram comes up every time you see one of these things. So this here is going to be 40 sine 30. And notice that I now know it's a negative 40 sine 30 because it's on this stretch diagram. I get my sines from the stretch diagram. I don't look at this other diagram for the sines for my equation because it's got that bend in it. So I can say, okay, find T using. Now it's up to me which one I use. The sum of the forces on the 6 is equal to the mass of the 6 times the acceleration of the 6. Then I don't have to worry about this 40 sine 30, but I'm going to have to deal with it sooner or later, so it doesn't matter which one you pick. So I look at this diagram, I say plus 60 added to minus T is equal to 6 times A. So T is equal to 6A, whoops, no, 60 minus 6A. I took the T to the other side, I've got to take the 6A to the other side. Oh, if only I knew the A. Find A using. Well, I've used the 6 up, and I don't think the 4 is going to be any better. I've got to find something where there's no T involved. I've got to make T an internal force. That's really what I'm doing. I can ignore T because I'm making it an internal force. And it's the sum of the external forces that equals MA. Yeah? Remember that thing about sitting in your car seat and pushing on the dashboard does not accelerate your car because it's an internal force. So I'm very cleverly making T an internal force, so it's no longer in my equation by taking the system. That's why I take the system. And I say the sum of the forces on the system is equal to the mass of the system times the acceleration of the system. So I say plus 60 added to minus 40 sine 30 is equal to 4 plus 6 times A. So A is going to equal 60 minus always check that you're in whatever you want to be in, and I want to be in degrees, so I'm in degrees. 40 sine 30 equals 20, should have known that, 20 So that's going to be 60 minus 20 over 10. 4 plus 6 makes 10. So that's going to be 60 minus 20 is equal to 10a. So a equals 60 minus 20 over 10, which is 4 meters per second squared. And just for form's sake, we'll say A4 equals A6 equals a system, just so we know. And so we get I'm going to say, well, in that case then T is equal to 60 minus 6 times 4. T is equal to 60 minus 24. T is equal to 36 newtons. So same idea. It's the same problem, we just had to find out this backwards component. When we have friction, it will be the same problem, but we have to find out the frictional force. That's the way it's going to be. Okay? Questions on that? Very standard. It's a bit formulaic. It's like, you know, the layout really helps. Doing the stretch diagram is really, I think, is really important. It's the essence of the thing. There's more than one way to do it. If you look online, you'll see other ways to do it, but this is, I think, the most efficient way of doing it. Okay, so which trace best represents the relationship between frictional force and the normal force of an object that is moving? So I'd say FF is equal to mu k times Fn. That's linear, isn't it? There's FF. There's Fn. Mu k is a constant. That's y is equal to constant x plus b. That's linear. So, and you know that as Fn gets bigger, Ff gets bigger. So it's that linear. It's not that linear. And if you don't get that, what you can do is you can just say, well, let's plot Ff versus Fn. And we go, let Fn equal 0, 1, 2, 3, 4, 5. And then for this constant, why not call it 1? Call it 1. Why not call it 1? Just make life easy. It's constant. So 1 times 0 is 0, 1 times 1 is 1, and 1 times 2 is 2, and 1 times 3 is 3, and 1 times 4 is 4, and 1 times 5 is 5. So if I plot my own little graph of FF versus Fn, and I go 1, 2, 3, 4, 5, and I go 1, 2, 4, 5, so that's 0, and that's 5, and that's 0, and that's 5. And this is in newtons, and this is in newtons. And I go 1 and 1 and 2 and 2 and 3 and 3 and 4 and 4 and 5 and 5. There's my slope. So the skills, when you were doing physics, no, you are doing physics 1. When you started physics 1, the skill I wanted was you could actually spot which of these traces best fits the relationship. Later on, I'd like to be able to ask you to plot me a graph. And I give you the grid, I give you the axes, and that's it. And what I find is sometimes people will just freak because I didn't give them any numbers. And that's part of the skill I want to develop, is that so you can say, oh, I'm going to let k equals 1, I'm going to pick 0 to 5, and I'm going to do it, and I'm confident in plotting a trace out, because that's a skill that's really useful to have. And people are just very uncomfortable if you're not given the actual numbers people just, when they first begin, feel very uncomfortable with that. But that's why we kind of like, we're gonna practice it. And then this next one is a so-called ratio problem. Another skill that I think is really useful. So this says a block slides across a level table. The force of friction between the block and the table is 6 newtons. What would be the new force of friction if the mass were doubled, or mass was tripled, and the coefficient of friction was something else? Yeah. And people can sometimes do these in their head. There are some people walk around and they can look and they go, oh, that's going to be 25. But not many people can do that, and you've got to show work. So I think layout's really important in this as well. So the first thing you do, you say, well, what governs this? And it's slides across. FF is equal to this kinetic friction, mu k times Fn. That's my relationship. And it's a ratio, so I can say my FF new over my FF old is equal to, oh, and I know FF old. That equals FF new over 6. And that equals mu k new Fn new over mu k old Fn old. Now, I've not given you Fn. I gave you the masses. But you can see that, you know, if that's if that's Fg, this is Fn. And it's on a level table, so they're just equal and opposite. So this would be mu k new over mg, mass new g new over mu k old, mass old g old. Just taking the two relationships and putting new over old. It's always good to put new over old. So I say FF new over 6 is equal to, I don't know the value of mu k, but I do know it was quadrupled. So whatever number I decide to put in for this old value, it's got to be 4 times bigger. That's what quadrupling is. If you're not, well, even if you're a language, even if you're a native speaker, just so it's all fair, but I understand that people will sometimes get confused between quadrupled and quartered and stuff like that. If you ask me a question like that in the test, what is quadruple? I'll gladly tell you that. I won't tell you what mu k is, and I won't tell you what Fn is and all that. There's the technical stuff I won't tell you. But I have had some, especially non-native speakers, who get tripped up on some of the just language that it's not made a big deal out in the book, because the book assumes that you know that kind of language. But you don't, so, you know, if in doubt, ask me. If the worst that will happen is I'll say I can't answer that question, you know. But don't sit there and you know, be stumped because of some colloquialism that you don't know. If it's a technical term, you're on your own. But if it's like that, I don't mind that. So the easiest way is to say the old one was 4 and the old one was 1 and the new one's 4. That's quadrupled. And then we go to mass. Well, the mass is tripled. So the easiest way to do that is to say 3 and 1. And it says nothing. about G. You didn't move to another planet. But you could have done. If you didn't move to another planet, if you want, you can put 10 and 10 down because that's the value of G. But I didn't even say you're on Earth. I just said nothing about it. You could put down G and cancel it. But frankly, I'm in the habit where I just put down 1 and 1. For anything I don't know, I call it 1. And that equals 12. And I can't tell you how many students will tell me that the answer is 12 newtons. And I'll look at their work and they're not writing out equations. They're doing mathematical phrases. There's a cluster of numbers over here, there's some letters over there. Here's the catch. FF nu over 6 equals 12. So FF nu is equal to 12 times 6, which equals 72 newtons. There's your answer. And I can't tell you how many people stumble at that last little step. Just they're not writing in equations. So you look at your work, and if you're in the habit of putting down numbers, doing a calculation, but you're putting down numbers. You're not saying something equals something. You're just doing the you know. You're not saying A equals B. You're just calculating what B is. Then that's where you can come adrift because you're not putting the complete sentence down. We want you to put complete sentences down. So it's interesting. It's a ratio thing. Oh, sorry, we'd already done that before. So, I'm sorry. So statics with friction. Let's do some statics with friction. How am I doing for time? Not bad. Horizontal applied force of 8 newtons causes a 2 kilogram block to slide at a steady speed of 7 meters per second across a level table. Okay, so I got my visualization. I can say FF is equal to mu k times Fn. That's one possibility. On my diagram, I know that that's FF. And I know that that's Fn, and that's going to be 20, because it's a level table. So then mu k is equal to FF over Fn. I don't know either one of them. So let's find them. Find FF using the sum of the forces on the green line is equal to steady speed. Oh, 0. It's not accelerating. It's moving, but it's not accelerating. Where am I going to put my green line? I want to find FF, so I want to ignore Fn. So I'm going to put my green line like that. Put your green line perpendicular to what you want to ignore. There's two unknowns, FF and Fn. I want to separate them. So I'm going to look at my diagram and I say plus 8 added to minus FF is equal to 0. So FF is equal to 8 newtons. A bit pedantic, you might have been able to just see that by observation. Find Fn using the sum of the forces purple line equals 0, because it's not accelerating up into the air or down into the ground. I want to find my Fn, I don't want to find Ff. I say plus Fn added to minus 20 is equal to 0, so Fn is equal to 20 newtons. Combine these two guys together. I say mu k is equal to Ff over Fn, which equals 8 over 20, which equals 0.4 newtons. Whoa, bad Bonaquisti, 0.4. Nothings. It's got no units, because newtons over newtons is nothings. Can you see how what we've practiced so far has just been used here? It's like resolving forces in a given direction, trying to solve in one step, unable to solve in one step. What do I need? Oh, I need Fn and I need Ff. Let's pick one of those, Ff. I've got to resolve my forces in one direction. I want to avoid Fn, so go perpendicular to Fn, solve for Ff. Want to find Fn, go perpendicular to Fn, solve for Ff. Just same skills, just put together in the package. Similar question, but not the same. A 3 kg rock is stationary, but on the point of slipping, what is the coefficient of static friction? It's 20 degrees. Little block, big arrows is always better. There's got to be friction, otherwise this thing's going to accelerate. So this is going to be Ff. Mu is equal to Ff over Fn. Did I do that right? Yep. Find Ff using, let's change colors so you can see it. The sum of the forces, green line equals 0, because it's on the point of slipping, but it's not slipping. And my green line, I don't want to have Fn in my expression, so I'm going to pick a line that is perpendicular to it. It's not defined by what I want, it's defined by what I want to get rid of. And that is going to be 30 sine 20. I visualized my component. I formed the triangle. I did my trig. This is its own component. It's in its own green line. Make that end positive, make that end negative. It doesn't matter which way around you do it. And we say plus Ff added to minus 30 sine 20 is equal to 0. So Ff is equal to 30 sine 20. I'm going to leave it in that form because I know the answer and I want to show you something. find Fn using the sum of the forces on the purple line equals 0. Where am I going to put this purple line? I want to ignore FF, so now I go perpendicular to FF. I resolve this weight along this purple line, and this would be 30 cosine 20. And this is its own component. I say, let's call this positive and this negative. I say plus Fn added to minus 30 cosine 20 equals 0. So Fn is equal to 30 cosine 20. Mu is equal to FF over Fn, which equals 30 sine 20 over 30 cosine 20, which equals tan 20. The 30s cancel. Opposite over hypotenuse divided by adjacent over hypotenuse is opposite over adjacent, which is tangent. Check them in degrees. Go tan 20, which equals 0.3639, and again, no units. Can you see a lot of little steps? Nothing's new. We've done all the elements before. We just put it together. That's what we do for about the next week or so, maybe next 2 weeks, is we just use this same old stuff. F equals ma, F equals, sum of the forces equals 0, mu equals FF over Fn, used just over and over and over and over and over again in different forms. We're digging deep here. We're doing lots of applications of the same thing. So there it is. Good diagram. A bad diagram will hurt you. A good diagram will help you. If you can look at your diagram and you can say, there's a little angle, which means that's a little angle. So 20 here is 20 there. If you can see it, if it's all 90, if it's all at 45 degrees, and you have big blocks with little arrows, it's not helping you. So big arrows, little blocks. Start with a protractor, get the angles right. It will really help. When you get comfortable, you can slack off a bit, but start with a protractor. Make sure it looks right. And then just having confidence. The difference between you and me is often that I'm more confident because I've done it for 20 years. So I don't second guess myself so much. I still make slips, but not so many. I've learned how to avoid making slips more often. But I have faith in my methodologies. I know the principles. I don't try to remember problems. I can't remember the answer to any of these things. But I know the methodologies. And what I'd love you to do, and it takes kind of guts, is to try and let go of memorization of problems and start to embrace memorization of approach. You know, because once you have the approach right, the rest is just sums. And I'm not being insulting by that. I'm not minimizing what you have to do. But the bit you have to do is getting the right math. You know, getting the math on the right problem. It's not the math that catches people out most of the time. It's the doing good math on the wrong problem because they misinterpret the question. So, okay, so statics with friction. We've done the slope. We've done. How are we doing for time? Yeah, I got time. I want to add one. I'm going to find another blank page if I have one. Yes, I do. Oh, I'm sorry. Let me just go ahead because I'm dynamics with friction. Let's do this. Okay, so we have the table, but now there's a bit of friction involved. These masses are free to move. So we have a table. We have a 2 kilogram. We have a, is that an 8 kilogram? It looks like an 8 kilogram. Tension. Oops, the daisy. Tension goes that way. Tension. 80. This is 20. That's Fn. Stretch diagram. Tension. Tension. There is a frictional force. I know that because there's a coefficient of friction. I need to try and find that frictional force. I say Ff equals mu Fn. Ff is equal to 0.2 times 20. Ff is equal to 4 newtons. Can you see where that comes from? Did this little side calculation. That gives me that this guy equals 4. Let's have a look. Find the, what is the tension? Find T using the sum of the forces on the 8 is equal to the mass of the 8 times the acceleration of the 8. Plus 8t added to minus t is equal to 8 times a. So t is equal to 8t minus 8a. If only we knew the a. Sum of the forces on the system equals the mass of the system times the acceleration of the system plus 80 added to minus 4 is equal to 2 plus 8 times a. 76 is equal to 10a. A is equal to 76 over 10, which equals 7.6 meters per second squared. T is equal to 80 minus 8 times 7.6, which equals 80 minus bracket 8 times 7.6 close brackets is equal to 19.2. There we have it. It's the same old, same old. Now I'm just like making you work for the backwards force. I will not give you on a test a sloping friction-filled surface. I'll give you a sloping, or I'll give you friction-filled on the horizontal, but I won't give you both. It's just it makes it long, and you know, it's kind of like, I'd sooner give you two shorter problems than one long problem like that. I need not ask you for mu. I'm trying, I'm sorry. In those previous problems, we asked for mu. I might not ask you for mu. I might ask you for FF or FN, you know. I don't always ask you for the longest bit. I might just ask you for A, and don't get fooled into thinking I can't do that because I practiced doing T. You're finding A in the process of finding T. That's the purple bit, finding A. So don't miss an easy question because you're forever looking for the hard question. It's dynamics. It's on a slope. A 3 kilogram block accelerates at 1.5 meters per second, pointing down a slope. This thing is accelerating going down the slope. What is the coefficient of static friction? Oh, it shouldn't be static friction. Coefficient of kinetic friction for the block and the incline. F is equal to mu k times Fn. Mu k is equal to Ff over Fn. Find Ff using, I got to go back to my diagram. It's not complete. I have 30. I have normal force. Which way will my frictional force point? Is it up the slope or down the slope? Up the slope, because it opposes the tendency to motion, or the motion itself. And we are moving. We're not just moving, we're accelerating. Using the sum of the forces, I want to change colours. Let's do this in that green. The sum of the forces along the green line equals MA. Now, here's the tip. Whenever there is an acceleration, go with it. The acceleration is down the slope, so go with it. That guy is along the slope. This guy is along the slope, and this guy here, I'm sorry about this, it's 30 sine 30, and I try not to use the same number for the weight and the angle, but I did there. And also, by the way, this guy is along the slope. Yes, Cohen?
Isn't it 20?
Oh, 20. Oh, thank you. 20. Shame on me. I'm rushing a little bit, so I'm making mistakes. Okay? So what I say is, got to pick signs. Positive, negative, plus FF added to minus 30 sine 20 is equal to, not 0, but 3 times, what am I going to write in for my acceleration? Why is it negative 1.5? Because I chose to make the right-hand way positive and the left-hand way negative, and the language says down the slope. I'm pointing down the slope. It's telling you you're accelerating down the slope.
How could you choose to swap now? Could you do it differently?
If I had another force pointing upwards and the two of them were battling, you wouldn't know which way it was. If I added another force pushes up the slope, you don't know which is which, but if I can tell you it's down the slope, then you got to get your sign convention. Yeah? So if there was another force pointing upwards, you'd have to say which is the bigger force, and it'd be a different problem. But I could make it so that the frictional force is so that the acceleration is up the slope. But I'd either have to tell you that in words, or you'd have to be able to figure it out, but you'd have to use the right sign convention. Can you see how, without a diagram, you're done on this? Just forget it. No point. Because you won't get the signs. So then we say, okay, FF is equal to 30 sine 20 minus, I think that's 4.5. So FF is equal to, how am I doing for time? Ooh, gotta go. 30 sine 20 is going to be 10.26 minus 4.5 is equal to 5.76. And then I've got to pick up the pace a bit because I want to get this thing set. So now I've got to find Fn. I don't want to deal with FF. Find Fn using the sum of the forces on the black line equals 0. Because there's no acceleration in that direction. And I have this guy. And I have that guy. And this here is 30 cosine 20. And this is Fn.
That's negative.
So I'm going to make that positive and make that negative. I say plus Fn added to minus 30 cosine 20 is equal to 0. So Fn is equal to 30 cosine 20, which equals 30 cosine 20 is equal to 28.19. And then just to rush through this, so mu is equal to FF over Fn, which equals 5.76 over 28.19, which equals 5.76 divided by 28.19 is equal to 0.204. And there we have it. Just one last little check about how much time I have.